back. Today we're going to continue our exploration of matrices and introduce a very handy tool that is used for the analysis of matrices and also several other important things once we start talking about vector spaces a little later. And this analysis method is known as reduced row echelon forms of matrices. So it's in sense some classifications of matrices. So we say that a matrix A is to be in row echelon form, not reduced, we'll get to that in a moment, but just row echelon form if two requirements hold for that matrix. One, every all zero row are at the bottom of that particular matrix. Second, if the first non-zero entry of row K is in column J, then the first non-zero entry of the next row must be in a column farther to the right than the column that the preceding row's leading coefficient was existent in. Let's look at a few matrices and see if these matrices are in row echelon form. So example 1. Suppose we have the matrix 0, 0, some number, some number. I'm going to be using x's just to notate some non-zero number. So is this in row echelon form? The answer would be no, because the all zero rows should be at the bottom of this matrix. So the next question is this. Is the following matrix in row echelon form? XX, 0, 0. The answer is yes. Why? So requirement 1 mandates that the all zero rows are at the bottom, and the next requirement is that the first leading coefficient is located in a column farther to the right of the preceding entry. Notice the first leading coefficient is located there, but the next row doesn't have any leading coefficients, so by default this is going to be in row echelon form. The next matrix, consider x, x, 0, and x. Is this in row echelon form? The answer is yes. So why is that? So notice there are no all zero rows, so the first one by default checks out. The second, the leading coefficient of row 1 is there, and the leading coefficient of row 2 is in the next column to the right, which is farther, of course, than column 1, so that checks out as well. Scenario 4. Suppose we have 0, x, x, and x. Is this in row echelon form? Take a moment and think. The answer would be no. So there are no all zero rows to consider, so that by default checks out, but notice that the leading coefficient of row 1 is located there, and that's to the right of the next leading coefficient. They should be reversed. So if we were to do a row swap with row 1 and row 2, that would put this in row echelon form, but in its current state, this is not in row echelon form. 5. Suppose we have the matrix XXXX. Is this in row echelon form? The answer, no. So again, there are no all zero rows, so that by default checks out. The leading coefficient of row 1 is located there, and the leading coefficient of row 2 should be farther to the right than column 1, but the leading coefficient of row 2 is located directly under the leading coefficient of row 1, therefore that violates the second requirement, therefore that's not in row echelon form. The next matrix, consider this, 0, 0, 0, 0. Is that in row echelon form? Think about it. The answer, yes. All of the all zero rows are at the bottom of the matrix, but technically there are no non all zero rows. Technically the bottom and the top are the same exact thing by default. Also, since there are no leading coefficients to compare, this also by default satisfies requirement 2. So this is a very extreme case of a row echelon matrix. Scenario 7. Suppose I have x, 0, 0, x. So a diagonal matrix. Is this in row echelon form? The answer is yes. There are no all zero rows, so that by default cancels out. Our leading coefficient for row 1 is in column 1, and our leading coefficient for row 2 is in column 2, and 2 is bigger than 1, so that satisfies both requirements. The next scenario, suppose I have 0, x, and 0. Is this in row echelon form? So this scenario sort of looks like scenario number 4, except we have a 0 in that bottom. So it's almost like a mirrored symmetric matrix, or a mirror diagonal matrix, because it's on the off diagonal. So that would be no. The 0 rows isn't the problem here. The issue is the leading coefficients, because the leading coefficient of it is there, and the leading coefficient of the second row should be somewhere to the right, but it's somewhere to the left instead, so that violates that assumption. So those are some of the different rearrangements of at least the 2x2 scenario for identifying row echelon matrices. And of course, matrices don't have to be square in order for it to be in row echelon form. Let's define a new concept. So let us suppose that A is in row echelon form, so REF. Then the number of pivots, PIVOTS, of the matrix A is the number of leading non-zero entries across all rows. So let's consider some row echelon form matrices. So example 1. Suppose we have x, 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 0, x, and x. So that is in row echelon form, and you should be able to identify it. So where are the leading coefficients? So the leading coefficient is there, and the leading coefficient is there. So since those are the leading coefficient across all rows, the number of pivots that we have in this matrix is going to be equal to 2. So the number of pivots is equal to 2. Consider this matrix. X, 0, x, 0, 0, x, 0, 0, 0. You should be able to verify that this is indeed in row echelon form. All 0 rows are at the bottom, and our leading coefficients are in left to right order. So again, in this particular case, the number of pivots is again equal to 2. Notice there's not a pivot associated to column 2, and that's perfectly okay. It happens. And let's look at this example. X, 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 0, x, x, and 0, 0, x. So how many pivots does this matrix have? So notice that our leading coefficients are located on the diagonal this time, and that's okay too. So that means, let's stay consistent with our colors. So the number of pivots is going to be equal to 3. And maybe you could even give me an example of a matrix that has 1 pivot, or even a matrix that has 0 pivots. I'll let you think about that for a moment. So let's state a possibly theorem, I guess you could say, that you should be able to verify on your own. If the number of rows of A is m, so m rows, then the maximum number of pivots of A is equal to m. So if you only have m rows, you can't have more than m pivots. But of course you can have less than m pivots, like m minus 1, m minus 2, or even 0 pivots in a particular matrix, but the maximum number of pivots you can have in a matrix is going to be equal to the number of rows you have in that matrix. Now the next observation actually poses an issue with row echelon forms of matrices. In particular, row echelon forms of matrices are not unique. As an example, suppose we have the matrix A, which is equal to 3, 9, 0, 4. This matrix is, in its current form, in row echelon form. But, for example, if we do row 1 divided by 3 and row 2 divided by 4 to define, for example, new row 2 and new row 1, we get another row echelon form. In particular, we're going to have the matrix 1, 3, 0, 1, which is also in row echelon form. So if I say, what is the row echelon form of this matrix A, there's actually infinitely many answers for which you could give me, and that sometimes poses an issue. So what is the remedy for this? Impose a couple more requirements on that form, and that is where the reduced row echelon form comes in. And some people will just abbreviate that as RREF. So what is the requirements of a reduced row echelon form for a matrix? So requirement 1, A must be in row echelon form. So it requires all the 0 rows to be at the bottom and all of our leading coefficients of our non-zero rows to be stacked from left to right. Second, all of the pivots must be equal to 1, right? And that should reminisce from Gauss-Jordan elimination. And 3, all columns with pivots or with a pivot must have zeros in all other rows of that column. So if you have a 1 in a row, there must be zeros above it and also below it. Let's look at a few examples of reduced Row-Echelon forms of matrices. So scenario 1. Suppose I have x, 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 x. Is this the reduced Row-Echelon form? The answer is no. First off, it's not in Row-Echelon form because the leading coefficients are stacked on top of each other, and we know that's already a bad thing. Suppose we have x, 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 and 0, x, x. Is this in Row-Echelon form? The answer is no. Because, again, this is in Row-Echelon form, but it's not in reduced Row-Echelon form because those must be equal to 1, and there must be a 0 located there, right? So that imposes the next two requirements of reduced Row-Echelon form. So that is, of course, no. Consider this scenario. 1, x, x, 0, 1, x. Is this in reduced Row-Echelon form? Again, no, because this needs to be equal to 0. So for example, I would multiply that second row by whatever coefficient that is, subtract it from that number, and that should cancel it out. So that would be no. 4. Suppose I have 1, 0, x, 0, 1, x. Is this in reduced Row-Echelon form? The answer is yes. You should be able to check that all those requirements are held. 5. Suppose I have 1, 0, 0, 0, 0, 1. Is this in reduced Row-Echelon form? The answer is yes. Notice that our leading coefficients are stacked from left to right. All of the columns that have those pivots have zeros everywhere there. And all of our non-zero rows are existent at the bottom, but of course that doesn't apply here. And it is, of course, in Row-Echelon form, so all is good. So that is in reduced Row-Echelon form. Next scenario, what if I have 1, 5, 0, 0, 0, 1? Is this in reduced Row-Echelon form? Take a moment and think. So notice our leading coefficients are there. Those are our pivots. Notice that there are zeros located everywhere else in those particular columns, so that checks out. All of our non-zero rows are at the bottom, even though they technically don't exist here. And that's all the requirements of reduced Row-Echelon form. Therefore, this is in reduced Row-Echelon form. What about the matrix 1, 0, 0, 0, 1, 1? Is this in reduced Row-Echelon form? Again, our pivots are going to be located at those two entries. All of our columns with those pivots have zeros everywhere else. There's no rows of zeros at the bottom. In those cases, those would be at the bottom, and that checks out for reduced Row-Echelon forms requirements. Okay. Now, what are some special properties about reduced Row-Echelon forms? Let's quickly list them out here. So, special property number 1. The reduced Row-Echelon form of a matrix A is unique. I'm not going to prove that here, but that's definitely a very, very useful theorem to know. Next, very important characteristic. If A is an m by n square matrix, and let's assume it has n pivots, then the reduced Row-Echelon form of that square matrix is actually going to be equal to the identity matrix. And you may want to sort of think about why that is going to be, and maybe even give it a proof if you have the ability to. Now that theorem actually ties into this next sequence of thoughts. So if the reduced Row-Echelon form of the matrix is equal to the identity, and hence it has n pivots, then the determinant of A, one can show, is not equal to 0, and also one should be able to show that the inverse of that matrix exists, right? So now we have several different things sort of tying into each other, and that's very, very useful. Now that we've discussed some important properties of reduced Row-Echelon forms of matrices and also how to identify them, let us go through an example to sort of see how to generate the reduced Row-Echelon form for a particular matrix. Suppose we have this 2 by 3 matrix A, and we want to find the reduced Row-Echelon form of this matrix. So what we need to do is we want to make that equal to 1 and that equal to 0. So we can do that via, for example, Gaussian elimination. So what operation will we perform here? So what we can do is we can do 2 times row 1 minus row 2 in order to generate our new row 2. Once we get that, we're going to have the new matrix 2 minus 1, 2, 0 minus 5 minus 3. Now the next thing that we have is to turn this into our pivot. So what we can do first off is multiply that by negative 1, and that's going to give us the matrix 2 minus 1, 2, 0, 5, and 3. Now what I can do is I can focus on that 5 and focus on that negative 1 in order to make that, for example, 0. So how would I go about doing that? So what I can do is I can do 5 times row 1 plus row 2 in order to generate a new row 1. Once I do that, that's going to give me the new matrix. So 5 times 2 is going to be 10 plus 0 is 10. 5 times minus 1 is going to be minus 5 plus 5 is 0. 5 times 2 is 10 plus 3 is going to be equal to 13. And then my last row is going to remain fixed. So once I have that, now my goal is to make these both equal to 1. So I can divide row 1 by 10 and row 2 by 5. Therefore, we're going to have the new matrix 1, 0, 0, 1, 13 tenths, 3 fifths. Therefore what? That means the reduced Row-Echelon form of the matrix 2 minus 1, 2, 4, 3, 7 is equal to the matrix 1, 0, 13 tenths, 0, 1, 3 fifths. Right? And keep in mind, this reduced Row-Echelon form is unique. Therefore, regardless of how you approach that Gauss-Jordan elimination process, you will get the same exact answer regardless. Once we know how to find the reduced Row-Echelon form of a matrix, we can actually analyze that matrix from a variety of different perspectives. So here is going to be two terms that we're going to be focusing on a lot once we start talking about the theoretical aspects of linear algebra. The first is known as the rank of a matrix, which is going to be denoted by rank of A. So the rank of a matrix A is actually going to be equal to the number of pivots in A. And the nullity of a matrix, which we're going to be represented as just NULL of A, is the number of columns in A that do not have a pivot. So let's look at our particular matrix that we were working with just a moment ago. So remember that we were able to represent a matrix A in terms of its reduced Row-Echelon form, and we were able to get 1, 0, 1.3, 0, 1, and then 0.6. So this was the reduced Row-Echelon form of A, and we were able to identify that our pivots are located there and there. Keep in mind that this matrix has 3 different columns. So how many pivots does this matrix have? Well, we see that the number of pivots are circled in green. They're located in columns 1 and 2. Therefore, the rank of the associated matrix A is going to be equal to 2. Now the nullity is the number of columns that do not have a pivot. So 3 columns total, 2 columns have a pivot. Therefore, how many columns do not have a pivot? Therefore, the nullity of this matrix is going to be equal to 1. From these definitions, you should be able to prove the following statement, in particular the rank of a matrix A plus the nullity of a matrix A is always going to be equal to the number of columns of A. And that should be a very straightforward proof in case you want to give it a go. Now there are some other theoretical aspects that you definitely should understand when it comes to the rank and nullity of a matrix. So let's define a couple more things. So definition 3. So if A is an m by n matrix and the rank of that matrix A, let's call it equal to T, then the following things hold. 1. If T is equal to M, so the rank of A is equal to the number of columns. That should be equal to N, not M. Right? So if T is equal to the number of columns in that particular matrix, then we say A has full rank. And if T is less than M, then we say that A has a rank deficiency of n minus t. So the rank deficiency is actually equal to what? That's just actually the nullity of that particular matrix A. Okay, so rank deficiency, nullity can be viewed as synonymous if you want them to be. Now, a very nice theorem that I'm not going to prove is the following. So theorem, the rank of a matrix A is actually equal to the rank of its transpose. Now this might come maybe not obvious, but it definitely is true. And I invite you to give that a shot in terms of a proof. Let's look at a little example to sort of see how that works. So let's assume A is the matrix 1, 0, 4, 0, 1, 6. So already A is in reduced Row-Echelon form, and the rank for this matrix will be equal to 2. Now if we look at the transpose of this, A transpose, so the first row is going to become the first column, so 1, 0, 4. Then we're going to have 0, 1, 6, right? So keep in mind, these are the pivots of A, right? And notice that they're actually going to be the pivots of A transpose, because this pivot is going to be able to eliminate that element. This pivot is going to be able to eliminate that element, just giving us a bunch of zeros at the beginning. So we can clearly see the reduced Row-Echelon form of AT is going to be equal to 1, 0, 0, 1, 0, 0. And again, the rank of A transpose is going to be equal to 2. In some sense, that actually is a sketch of the proof for this generalist theorem, but I'll let you get into the little details just in case you're interested in looking into that. Now, what is the nullity of this matrix A? So notice I have 3 columns, I have 2 pivots, therefore the nullity of that matrix is equal to 1. And notice the nullity of A transpose is going to be equal to 0. So the nullity of a matrix and its transpose are not equal to each other, but maybe you can come up with a nice relationship between the nullity of A and its transpose. A couple other theorems that are definitely useful in some certain circumstances. The rank of a M by N matrix is always less than or equal to the minimum of M and N. And I'll let you sort of think about what that means and why we should care. And this, if you're familiar with the triangle inequality, this is also true. The rank of A plus B is always less than or equal to the rank of A plus the rank of B. So we're looking at 2 matrices and their sum and the rank of those associated matrices. What I want to do now is introduce how rank and nullity sort of play a part of the solving systems of equations narrative. So let us assume we have this system of 2 equations and 4 unknowns. And let's actually just write this in matrix form. Let's write this as 3 minus 2, 5 minus 1, 7, 4 minus 7, 1, augmented with 7 and 1. So that's our augmented matrix. And let's actually call this augmented matrix, let's call this A. So one can find the reduced Row-Echelon form of this matrix A is approximately equal to 1, 0, 0, 1, 0.23, negative 2.15, negative 0.08, 0.38, augmented with 1.15. That doesn't look like 1.15. 1.15, and negative 1.77. Right? So that's going to be the reduced Row-Echelon form of that augmented matrix. So one can say, what can I sort of get out of this information? So notice there is our pivots, so therefore the rank of our original augmented matrix is going to be equal to 2. And generally speaking, we only talk about the rank of the left-hand side of a augmented matrix most of the time. And in terms of the nullity, since we have 4 columns of our coefficient matrix and we have a rank of 2, that means the nullity of that matrix is equal to 2. Now, what can we say about the variables x3 and x4 that are associated to the columns for which a nullity exists? So now let's introduce another definition. So definition, we say that all variables not associated to a pivot column In this case, that's going to be x3 and x4, are called free variables. Free variables, right? Now, why exactly do we call them free variables? Once we start looking at the applications of systems of equations and matrices, why we call them free variables is actually going to make a lot more sense, but right now we're just introducing the terminology that we're going to be using in those applications. Now, the number of free variables, so how can you quickly determine how many free variables you have? From this little diagram I've just shown, you should be able to tell me right now. So the number of free variables in a system whose coefficient matrix is A is equal to the nullity of that coefficient matrix, right? Because the nullity corresponds to the number of columns that do not have a pivot, and by definition, the number of columns that do not have a pivot, or the variables that are associated to those columns, are called free variables, right? So you can quickly determine how many free variables you have by looking at the nullity of that matrix, and of course the rank of that matrix are associated to the variables that are associated to columns with pivots in them, and usually we can represent the solutions of a system in terms of, for example, in this case, we can solve for x1 and x2, but x1 and x2 need to be represented in terms of x3 and x4, right? Now, what exactly does that mean in terms of columns 1 and columns 2? Do they share any relationship, or are they completely what we call independent of each other? And what does that mean about columns 3 and 4? Does that mean that 1 and 2 have a relationship with 3 and 4? Does 1 have a relationship with 3 only? Does 2 have a relationship with 4 only? Like, what can we really say about the relationships that are associated to free variables and those that are associated with columns with pivots? We'll discuss these questions at a later time, but for now, that's all for today. And I hope you enjoyed, and I'll see you in the next video. Take care.